This is SpaceTime Series 20, Episode 80, for broadcast on the 13th of October, 2017. Coming up on SpaceTime, a radio to pick up dark matter, a ring discovered around the dwarf planet Haumea, an asteroid 2012 TC4 zooms past the Earth. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Scientists are developing a new device which, instead of searching for dark matter particles, will search for dark matter waves. A report in the journal Symmetry by the United States Department of Energy's Stanford Linear Accelerator Center in Menlo Park, California, and the Fermi National Accelerator Laboratory Fermilab in Chicago, Illinois, claim a prototype's now being tested designed specifically to listen for the sounds of mysterious dark matter particles. Dark matter is an invisible substance thought to be 5 times more prevalent in the universe than normal matter. Although we can't see it, scientists know dark matter exists because they can see its effect on things like the rotation of galaxies. According to the most popular theory for dark matter, billions of dark matter particles, whatever they are, pass through the Earth every second. However, they're not detected because they can only interact gravitationally with normal matter. So far, researchers have mostly been looking for dark matter particles. Direct detection experiments for dark matter particles involve either searching for their signals or those of their daughter particles through particle collisions in atom smashes such as CERN's Large Hadron Collider, or alternatively in large underground detectors where scientists hope to see signals from dark matter particles colliding with detector material. Problem is, that'll only work if dark matter particles turn out to be massive enough to deposit a detectable amount of energy during the collision. Instead of looking for dark matter particles, the new research will look for dark matter waves using a kind of radio. One of the new device's developers, Peter Graham, from the Cavelli Institute for Particle Astrophysics and Cosmology, says if dark matter particles have too little mass, scientists might have a better chance of detecting them as waves rather than particles. And Graham's new detector will take the search in that direction. The so-called dark matter radio makes use of a bizarre concept in quantum mechanics known as particle-wave duality. The thing is, every particle can also behave as a wave. Take, for example, the photon. It's the massless fundamental particle which carries the electromagnetic force. Streams of photons make up the electromagnetic radiation or light, which are typically described as waves, including radio waves. The dark matter radio will search for dark matter waves associated with 2 specific potential dark matter candidates. These include looking for particles known as hidden photons, hypothetical cousins of normal photons, but with a small degree of mass. Another dark matter candidate is the axion. Axions are hypothetical elemental particles first postulated in 1977 to resolve the strong charged parity or CP problem in quantum chromodynamics or QCD. The theory of the strong nuclear force interaction between quarks and gluons. If axions do exist, and if they have low mass within a specific range, they could end up being a possible component of cold dark matter. Scientists think axions could be produced out of light and transformed back into it in the presence of a magnetic field. While the search for hidden photons will be completely unexplored territory, the dark matter radio could close some of the gaps in the search for axions. A regular radio intercepts radio waves with an antenna and converts them into sound. What sound depends on the station you're tuned into. Listeners tune into whatever station they want by adjusting an electrical circuit in which electricity oscillates at a certain resonant frequency. If the circuit's resonant frequency matches the station's frequency, the radio's tuned in and the listener can hear the broadcast. I recommend any station broadcasting SpaceTime. The dark matter radio works in the same way. At its heart is an electric circuit with an adjustable resonant frequency. If the device were tuned to a frequency which matched the frequency of a dark matter particle wave, the circuit would resonate. Scientists could then measure the frequency of the resonance, which in turn would reveal the mass of the dark matter particle. So the idea is to do a frequency sweep by slowly moving through the different frequencies, just like when you tune a radio from one end of the dial to the other. However, the electric signal from dark matter waves is expected to be very weak. Therefore, scientists are using highly sensitive magnetometers known as superconducting quantum interference devices, or SQUIDs, which they'll pair with extremely low noise amplifiers to hunt for potential signals. In its final design, the dark matter radio will be searching for particles with a mass range of trillionths to millionths of an electron volt. 1 electron volt is about a billionth the mass of a proton. Now, of course, this is somewhat problematic because the range includes kilohertz and gigahertz frequencies, which are already used for conventional radio broadcasting. Shielding the dark matter radio from unwanted radiation will be both important and challenging, involving copper sheeting several meters thick, or alternatively a significantly thinner layer of superconducting material. However, one advantage of the dark matter radio is that it won't be needed to be shielded from cosmic rays, whereas direct detection searches for dark matter particles need to operate deep down underground in order to block out particles raining down from space. Because of this, you can set up a dark matter radio in a university basement. Researchers are now testing a small-scale prototype at Stanford. They're using it to scan a relatively narrow frequency range, but they eventually hope to be operating 2 fully independent, full-size instruments. You're listening to SpaceTime. I'm Stuart Gary. Astronomers have detected another ringed world in our solar system. As well as the gas giants Jupiter, Saturn, Uranus and Neptune, the Kuiper Belt dwarf planet Haumea has now also been found to have a ring system. A report in the journal Nature claims a ring was detected around the unusually elongated lozenge-shaped world as it passed in front of a distant star. Named after the Hawaiian goddess of childbirth, Haumea has a diameter of around 1,920 kilometres. And it takes about 284 Earth years to complete one orbit around the Sun. Its highly elongated orbit ranges from around 35 to well over 50 astronomical units. An astronomical unit being the average distance between the Earth and the Sun, which is about 150 million kilometres or 8.3 light minutes. By comparison, Neptune, the most distant known planet in our solar system, is located about 30 astronomical units out from the Sun. And Pluto, the best-known Kuiper Belt object, has an orbit which ranges from just under 30 to just over 39 astronomical units. Scientists think Haumea's unusual shape could be due to its high rotational velocity, with the day on Haumea lasting just 3.9 hours. Haumea is also the third brightest object in the Kuiper Belt after the dwarf planets Pluto and Makemake, and it's easily observable with a large amateur telescope if you know where to look. For their observations, astronomers are using a battery of 12 telescopes at 10 separate observatories in order to study the dwarf planet to determine its density, shape and albedo or reflectivity. However, as they searched for signs of a possible atmosphere or exosphere around the dwarf planet, they instead discovered a 70 kilometre wide, 4,574 kilometre diameter ring. As well as its newly discovered ring, Haumea also has 2 small moons. The larger outer moon has a diameter of about 310 kilometres and takes about 49 Earth days to orbit the dwarf planet, while the smaller inner moon is only about 31 kilometres wide and circles the planet in just 18 days. You're listening to SpaceTime. I'm Stuart Gary. NASA's Juno spacecraft has completed its 8th close encounter with Jupiter, flying just 7,576 kilometres above the giant planet's swirling cloud tops. The new observations showed the planet's stormy south pole, revealing stunning colours and patterns swirling in the gas giant. Other images taken during this latest flyby have revealed spectacular auroral activity around the planet's north pole. As well as providing stunning new views of the gas giant's polar regions, the flybys also provided an opportunity for the spacecraft to observe Jupiter's 2 nearest Galilean moons, Io and Europa. Juno was launched back on August 5, 2011 from the Cape Canaveral Air Force Base in Florida, achieving Jovian orbit insertion 5 years later on July 4, 2016. The spacecraft's in a highly elongated 53 Earth-day polar orbit around the gas giant, designed to avoid as much of Jupiter's powerful radiation belts as possible. In fact, Juno's most delicate instruments are housed inside a special titanium strongbox in order to further try and protect them from Jupiter's destructive radiation fields. This highly elliptical orbit means Juno only spends about 2 hours physically transiting the planet's north pole to south pole every 53 days. During these flybys, Juno's instruments probe deep beneath the obscuring cloud cover, studying the planet's gravitational field and internal structure, its composition, weather patterns, atmosphere and cloud layers, auroral activity and magnetosphere, in order to better understand Jupiter's origins and history. The streams of data coming from Juno continue to astound scientists, who have already been forced to modify many of their pre-existing hypotheses about the solar system's largest planet. And scientists are now having to revise their ideas about Jupiter's internal structure and planetary core. It was originally thought that deep down below its thick, turbulent gaseous envelope, Jupiter would have had a solid, dense, rocky core, about the size of the Earth, surrounded by an exotic, metallic hydrogen mantle. Others, however, predicted the solar system's largest planet wouldn't have a core at all. Instead, the data from Juno indicates Jupiter's core may be somewhere in between these two hypotheses, a fuzzy rather than solid core structure, and far larger than anyone had anticipated. Juno principal science investigator Scott Bolton from the Southwest Research Institute in San Antonio, Texas, says the gravity data obtained so far isn't consistent with a small compact core or no core at all. But it is somewhat consistent with a large fuzzy core that may be partially dissolved. The data is also consistent with some deep motions or zonal winds dictating the interior of Jupiter's dynamics, which are very different from what previous models had assumed. To find out more, Andrew Dunkley is speaking with Dr. Fred Watson from the Australian Astronomical Observatory.
Now, Fred, we're going to revisit an old friend, that is the tiny little world that we know of as Jupiter. And we're going to focus on the Juno spacecraft. All the talk recently has been about Cassini splashing down in Saturn, so to speak. But in the background, Juno's been doing its thing. What's the latest?
That's right, Andrew. Yes, Juno arrived in the vicinity of Jupiter rather more than a year ago now. So I think it was July last year. And so it's been going through its mission. It's in orbit around Jupiter. It flies over the poles of Jupiter in a very elongated orbit. And the idea of that elongated orbit is to try and keep the spacecraft as far as possible out of Jupiter's radiation belt, which arise because of Jupiter's intense magnetic field. So we've got lots and lots of new information, and they've come from a special issue, I think, of Geophysical Research Letters, which has 44 papers coming from the Juno mission, as well as a couple of studies that have come from the Science Journal. So lots and lots of stuff floating around now, revealing the details of what we've found. There's a bit of a list here, so just going through it quickly. First of all, around Jupiter's North Pole is totally different from Saturn's, which has a strong high-speed vortex at the center, and then this enormous hexagonal jet stream around it.
Yeah, that's right.
Perfect hexagon. Looks as though you should be putting a spanner on it rather than observing it on a planet. Jupiter is nothing like that. It's just turbulent, an absolutely tumultuous area, oval-shaped cyclones, which are, they're huge. They're 1,200 kilometers across or something like that. So a very, very different regime near the North Pole of Jupiter from what we get in Saturn. And, well, that's a really quite hard thing to understand, because we think these two gas giants are rather similar in their structure, but apparently not, certainly not in their upper atmosphere. And then the one that I think is really baffling, one of the things that we have sort of hoped with the Juno mission is that by observing the way the planet distorts the orbit of Juno, we might be able to plot kind of what's going on underneath Jupiter's clouds, what's a sort of a world we're looking at. And there was always this thought that right at the center of Jupiter there will be a solid core, that because it's a gas giant, that doesn't preclude a solid core. And in fact, people have speculated that it may be something called metallic hydrogen, whose existence we do know, but we've never really seen it en masse. But it's really apparently not like that at all. The thinking now is that there is no distinct core. There's no place where you can say, well, 60,000 kilometers below the surface, it changes into a solid object. Apparently, it's not like that. There is a comment here from one of the scientists. We used to think that there was a little ball of heavy elements, small and quite distinct at the center. Now we're thinking that mass may be much more spread out. Maybe there was an original rocky ice core in the bottom, but it's being dissolved away because of the heat and the pressure, and maybe there isn't a liquid metal hydrogen core at the middle that is sharply differentiated from everything else. So a real question about what the inside is like.
Yeah, I suppose the difficult question to answer is, how do we really find out?
Probably other missions that people will cleverly put together to analyse that sort of thing. But Juno really is the best we've got at the moment.
It must be really frustrating, Fred, for them to launch a mission like Juno and get the equipment the way they want it, then go there and learn something that spacecraft is incapable of elaborating about.
Exactly.
Knowing full well that it's going to cost millions and millions of dollars and months and years to then send another spacecraft to find out the answer to the questions that have evolved.
It's really remarkable. Just moving on, there are questions that have been answered. The atmosphere of Jupiter apparently has similarities with the atmosphere of the Earth. On the Earth, we know that in the equatorial regions, you get these, what are called Hadley cells. There's a thing called Hadley circulation. It dates back to a 17th century astronomer, actually. And so winds blow in towards the equator. They kind of rise up and generate thunderstorms, and then the winds flow back towards the poles. There's this circulation in Jupiter's atmosphere. And this is similar, apparently, on Jupiter, much bigger cells, of course. And there's a comment here: instead of water, they rain out ammonia crystals that quickly evaporate. We know there's a lot of ammonia in Jupiter's atmosphere, but it's a surprise that it actually rains crystals in Jupiter's atmosphere.
Wow.
Then just moving on, the magnetic field's twice as strong as we thought it was. It's about 10 times stronger than the Earth. But perhaps finally, and one of the really interesting things, of course, the magnetic field is driven, as the Earth's is, by what we call dynamo effects. It's, circulation of essentially metallic or stuff that conducts electricity being circulated in a planet. In the case of the Earth, it's our iron core that causes the dynamo that gives rise to the Earth's magnetic field. But Jupiter's is really complicated, and apparently it's quite high up in the atmosphere of Jupiter, which means that the thinking there is that because Juno has seen very strong, small-scale variations in Jupiter's magnetic field, that might be what gives rise to the magnetic field overall. So we might be seeing the sort of granularity in structures near the surface of Jupiter that are giving rise to the magnetic field. Remarkable stuff.
Well, if it doesn't have a core, you can't say the core is the cause.
That's exactly right. That's right.
So there must be something else going on.
Lots going on, and it's up to us to find out what it is, Andrew.
And how long will Juno be in operation?
I think it's got another year or so. It's got a specific number of orbits, and then, of course, it will be plunged into the atmosphere of Jupiter, just like Cassini was, to avoid any kind of contamination of its moons.
Yeah, the Juno mission, the Cassini mission, they're sort of mapping out where we go next as far as exploration of the gas giants and the outer solar system is concerned. We've really achieved a lot in recent years when you think about it. Pluto and so many other things. There's been some astonishing revelations, really, Fred.
We're not doing badly, are we? And thanks largely to NASA, who run on a budget that really is, I think their budget should be doubled. It's not that adequate.
That's Dr. Fred Watson from the Australian Astronomical Observatory speaking with Andrew Dunkley on our sister program, Space Nuts. And this is Space Time. I'm Stuart Gary. An asteroid about the size of a house has just passed some 50,150 kilometres above the South Pacific Ocean, travelling at over 7.6 kilometres per second. Known as a NEO or near-Earth object, the asteroid, designated 2012 TC4, hadn't been seen since the week it was discovered way back in October 2012, when it sped past the Earth at about a quarter the distance between the Earth and the Moon. During the intervening 5 years, the space rock has been simply too faint and too distant to be detected. However, as it started to make its approach to Earth earlier this year, large telescopes began searching the skies looking for it in order to re-establish its precise trajectory. The new observations refined its size from the original estimation of between 10 and 30 metres, based on the original brightness measurements made in 2012, down to a more accurate 15 metres across. By comparison, the asteroid which hit Earth's atmosphere and airburst above the Russian city of Chelyabinsk back in February 2013 was roughly 20 metres across. More importantly, astronomers were also able to narrow down its orbital trajectory. Original estimates placed its closest approach somewhere between 6,800 and 270,000 kilometres above Earth's surface. Those calculations were based on just 7 days of tracking 2012 TC4 after its discovery back on October the 5th, 2012 by PanSTARRS, the Panchromatic Survey Telescope and Rapid Response System on the island of Maui in Hawaii. Back in 2012, TC4 passed 94,960 kilometres above the Earth 8 days after its discovery. The European Southern Observatory's Very Large Telescope, the VLT, caught sight of the asteroid on July 27th this year, allowing astronomers to begin an intense observing campaign to refine what they know about this wildly spinning space rock. The asteroid was some 60 million kilometres away at the time of recovery. Astronomers have since pointed both NASA's Goldstone Deep Space Network Tracking Station radar in California and the giant 305-metre Arecibo radio telescope dish in Puerto Rico, which was recently battered by Hurricane Maria, at the asteroid to unlock some of its secrets. Observations of TC4's light curve tells astronomers the asteroid appears to be elongated in shape, and it spins roughly once every 12.2 minutes, which is fairly typical for an asteroid of this size. The asteroid's closest approach to Earth was at around 1 o'clock in the afternoon on October the 13th, Australian Eastern Daylight Time. That's 10 p.m. October 12, US Eastern Daylight Time. At the point of closest approach, it was travelling southwards through the constellations of Capricornus and Sagittarius, moving across the sky at around 1 degree every 4 minutes. The Earth flyby was close enough for Earth's gravity to modify the asteroid's 609 Earth-day orbit around the Sun. NASA says its new orbital solution confirms that TC4 will not impact the Earth on its next close encounter in 2050, nor on the following one in 2079. So it looks like we're safe. At least for now. I'm Stuart Gary. This is SpaceTime. Sir Richard Branson says Virgin Galactic is still expected to begin space tourism flights next year. The company has been continuing flight tests on the first of its new suborbital spaceplanes, the VSS Unity. Earlier this year, the spacecraft successfully undertook testing of its feathered tailplane re-entry system. That followed a series of solo glide flights last year. Once operational, a fleet of about 6 of the Burt Rutan scaled composites-built Spaceship Two craft will be used for a mixture of suborbital tourist and science payload flights. The spaceplanes take off on a conventional runway mounted between the twin hulls of a White Knight 2 mothership, climbing to an altitude of around 40 to 50,000 feet. The spacecraft will then be released to ignite its rocket propulsion system and climb to an altitude of over 330,000 feet or 100 kilometres, the official start of space. Passengers will then experience several minutes of weightlessness and, of course, those spectacular views of the Earth below from the darkness of space, before re-entering the Earth's atmosphere and gliding to a conventional runway landing. I'm Stuart Gary. This is SpaceTime. A SpaceX Falcon 9 rocket has launched 10 Iridium NEXT communication satellites into orbit in what's expected to be a double header for the Hawthorne, California-based company. The Iridium 3 mission, the third SpaceX launch of Iridium satellites, blasted into pre-dawn skies from Space Launch Complex 4E at the Vandenberg Air Force Base in California. Following stage separation and upper stage ignition, the Falcon 9 core stage returned to Earth, successfully landing on the SpaceX drone barge Just Read the Instructions, positioned several hundred kilometres downrange in the North Pacific Ocean.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Operations and secure the pad editing.
GC copies. We'll go.
T plus 1 minute and 17 seconds into flight. Falcon 9
approaching max Q. MVAC-D chilling.
Chills begun.
We're now getting the second stage engine ready for ignition. Several activities coming up here very shortly. At T plus 2 minutes and 24 seconds, we expect main engine cutoff, followed immediately by stage separation and ignition of the upper stage engine. Right after that, the first stage will begin the first of 3 burns to return us back to the Pacific Ocean to the drone ship parked offshore about 300 kilometers downrange. Coming up on MECO.
We have MECO. We have back ignition.
T plus 2 minutes and 47 seconds into flight. We've had successful stage separation and ignition of the upper stage engine. We've also relit 3 of the engines on the first stage to begin the sequence that will return it to the drone ship in the Pacific Ocean. Boost back burn lasts about 30 seconds. And we have fairing separation. It's just before dawn as we head south over the Pacific Ocean.
Stage 1 entry startup.
We have startup. It looks like all 3 engines are up and running. Also, the grid fins did deploy. They'll now be used to guide us as we enter the Earth's atmosphere. And we've had shutdown of the entry burn.
Stage 1 AFTS has nuked.
The automated flight termination system, autonomous flight termination system has safed on the first stage. We're coming up on T plus 7 minutes. Stage 1 is headed back to the drone ship in the Pacific Ocean. Stage 2 still headed to its initial parking orbit. Shutdown of the second stage engine should be just over T plus 9 minutes into flight. Now we're getting ready for the landing burn of the first stage.
Landing burn start. Stage 1 landing successful.
Delta LS.
The SpaceX Iridium 3 mission was the 3rd Iridium mission this year, following previous launches in January and June. 5 more launches are planned through to the middle of next year, eventually placing a total of 75 next-generation Iridium satellites into orbit, in the process completely overhauling the company's communications satellite constellation. Built by Thales Alenia Space, the 860-kilogram Iridium NEXT satellites are each equipped with both Ka and L-band antennas. They're placed into one of 6 772-kilometre-high orbital planes spaced approximately 30 degrees apart. Each satellite has a 15-year lifetime. The launch was the 42nd Falcon 9 flight since the rocket design became operational in 2010. It was also the 14th Falcon 9 launch this year, a new record. And it was also the 4th SpaceX launch from Vandenberg this year. At the start of the story, we said the launch was the first part of a double-header. That's because the next Falcon 9 launch is slated for today. It'll see the SES-11 telecommunications satellite placed into orbit from the Kennedy Space Center's Pad 39A at the Cape Canaveral Air Force Base in Florida. And we'll bring you coverage of that launch next week. This is SpaceTime. I'm Stuart Gary. Astronauts aboard the International Space Station have just completed the second of this month's 3 scheduled extravehicular activities, or EVAs, NASA speak for spacewalk. The latest, lasting around 7 hours, involved regular maintenance work including lubricating components and replacing faulty equipment on an external camera. The first of the EVAs, which took place last week, involved replacing a component on the space station's Canadarm2 robotic arm. The crew's next spacewalk is slated for October the 18th. I'm Stuart Gary. You're listening to SpaceTime. China has launched a Long March 2D rocket carrying a new remote sensing Earth observation satellite for Venezuela. The flight blasted into orbit from the Jiuquan Satellite Launch Center in Inner Mongolia's Gobi Desert. On board was the second Venezuela remote sensing satellite built by China for the South American dictatorship. The 1,000-kilogram VRSS-2 spacecraft is built around a CAS 2000 compact satellite platform. The probe's equipped with a 1-metre panchromatic and 4-metre multispectral imaging system, as well as both 30-metre shortwave infrared and 60-metre longwave infrared images. The flight was the first launch of a 2-stage Long March 2D rocket since last December's failure of a Long March 2D carrying the SuperView 101 and 102 satellites. The 2 high-resolution Earth imaging spacecraft failed to reach their intended orbits. You're listening to SpaceTime. I'm Stuart Gary. And time now to turn our eyes to the skies and check out the celestial sphere for October on Skywatch. October is the 10th month of the year, and that may be confusing because octo in Latin means 8 rather than 10. The answer lies in the old Roman calendar, which had just 10 months before the addition of January and February. And that 10-month year is still reflected today, with the name September or septem being Latin for 7, November or novem 9, and December or deci meaning 10. Looking to the southwest this evening, you'll see the two bright pointer stars to the Southern Cross, the best-known constellation in the southern skies. The brightest, and also what looks like the furthest away from the cross, is Alpha Centauri, the nearest star system to our own solar system. Alpha Centauri is a triple star system comprising two stars, Alpha Centauri A and B, which are in a binary system orbiting each other, with the third star, Proxima Centauri, orbiting the pair. Like the Sun, Alpha Centauri A is a spectral type G yellow dwarf star. It's about 10% more massive than the Sun and about 1.5 times more luminous. Its binary partner, Alpha Centauri B, is a spectral type K orange dwarf star, a little bit smaller and cooler than its companion, with about 90% of the Sun's mass and about half its luminosity. This pair, Alpha Centauri A and B, orbit each other between 11.2 and 35.6 astronomical units. As we mentioned earlier in the show, an astronomical unit is the average distance between the Earth and the Sun, which equates to about 150 million kilometres or around 8.3 light minutes. So, the pair's orbit around each other varies by the average distance between Saturn and the Sun and the average distance between Pluto and the Sun. The two stars orbit each other over a period of 79.91 Earth years. The pair are located at an average distance of 4.37 light years from the Sun. Now, although that sounds like a measure of time, a light year is actually a measure of distance. And that distance is about 10 trillion kilometres, the distance a photon can travel in a year at the speed of light, which is about 300,000 kilometres per second in a vacuum and the ultimate speed limit of the universe. The third star in the Alpha Centauri system is the spectral type M red dwarf star Proxima Centauri, sometimes called Alpha Centauri C. Proxima Centauri is just 4.25 light years away, making it the nearest star to the Earth other than the Sun. It's loosely gravitationally bound to Alpha Centauri A and B, orbiting the pair at an average distance of about 13,000 astronomical units. That's about 0.21 light years, or to put that another way, it's about 430 times the size of Neptune's orbit around the Sun. In 2016, astronomers confirmed the existence of an Earth-sized terrestrial planet orbiting in the habitable zone around Proxima Centauri, making it the nearest known extrasolar or exoplanet to the Earth. The planet, known as Proxima b, takes just 11 Earth days to complete one orbit around its host star, far closer than Mercury's 88 Earth day orbit around the Sun. The second and slightly fainter of the two pointer stars is Beta Centauri. While Alpha Centauri is the third brightest star in the night sky, outshone only by Sirius and Canopus, Beta Centauri is only about the 10th brightest star. Turning to the southeast now, and you'll see a really bright blue-white star. That's Alpha Eridani or Achernar, which represents the southern tip of Eridanus, one of the largest and longest constellations in the sky. Achernar is located about 139 light years away. It's a binary star system comprising two stars, Alpha Eridani A and Alpha Eridani B. Alpha Eridani A is a young, hot spectral type B blue star, about 6.7 times the mass of the Sun, with some 3,150 times the Sun's luminosity. The companion star, Alpha Eridani B, appears to be a spectral type A white dwarf star, about twice the mass of the Sun. The two stars orbit each other every 14 to 15 years at an average distance of about 12.3 astronomical units. Because of its high rotation rate of over 16 kilometres per second, Alpha Eridani A is one of the least spherical stars in the Milky Way, spinning so rapidly that it's assumed the shape of an oblate spheroid, with an equatorial diameter 56% greater than its polar diameter. This distorted shape means the star displays significant latitudinal temperatures, with its polar temperature being around 20,000 Kelvin, while its equatorial temperature is closer to 10,000 Kelvin. That's because its equator is much further away from the stellar core compared to its poles. The high polar temperatures are generating a fast polar wind, which is ejecting matter from the star and creating a polar envelope of hot gas and plasma. Located between the south celestial pole and Achernar, you'll notice two fuzzy-looking clouds. Now, these aren't clouds at all, but rather two satellite dwarf galaxies which orbit the Milky Way, known as the Large and Small Magellanic Clouds. They're named in honour of Ferdinand Magellan, who became the first European to officially record them during his expedition to circumnavigate the Earth between 1519 and 1522. The bigger and nearer of the pair is the Large Magellanic Cloud, which is located about 160 light-years away. It's easy to spot about halfway between Achernar and the horizon. It's about 14,000 light-years across, roughly twice that of the Small Magellanic Cloud, which is located about 200,000 light-years from the Milky Way. By comparison, the Milky Way is about 100,000 light-years across. The two dwarf galaxies are separated by roughly 75,000 light-years. They were considered the closest galaxies to the Milky Way until the 1994 discovery of the Sagittarius Dwarf Elliptical Galaxy, and then the 2003 confirmation that the Canis Major Dwarf Galaxy is actually our nearest galactic neighbour. The total mass of the Magellanic Clouds is uncertain. Only a fraction of their gas seems to have coalesced into stars, and they probably both have unusually large dark matter halos. One recent estimate for the total mass of the Large Magellanic Cloud is about a tenth that of the Milky Way. The Magellanic Clouds have both been greatly distorted by gravitational tidal interactions as they're gradually being torn apart and absorbed into the Milky Way. These huge tidal forces have turned both Magellanic Clouds into irregular, disrupted, barred spiral galaxies. But gravity isn't a one-way street, with a combined gravitational force of both Magellanic Clouds also affecting the Milky Way, distorting the outer parts of our galactic disk. Through a good telescope, you can see streams of neutral hydrogen gas clouds and isolated stars, which connect both galaxies to each other and to the Milky Way. A clear example of galactic cannibalism at work. Now, if you look just above the Small Magellanic Cloud through a backyard telescope or a decent pair of binoculars, you'll see a small blurry dot. That's the 47 Tucanae globular cluster, a tightly packed ball of stars some 16,000 light-years away that were all originally formed at the same time through the gravitational collapse of the same molecular gas and dust cloud. Looking to the west and you'll see the bright reddish-orange supergiant star Antares, the heart of the constellation Scorpius the Scorpion. Above it you'll see a bunch of stars stretched out like a reverse question mark. That's the tail of the Scorpion. And just above and to the north of that, you'll see the constellation of Sagittarius, the Archer. Sagittarius shows the way to the supermassive black hole at the centre of the Milky Way, some 27,000 light-years away. This monster black hole, known as Sagittarius A star, has about 4.3 million times the mass of the Sun. Looking to the north-northwest is the constellation Lyra the Harp and its bright star Vega, the fifth brightest star in the night sky, and one of the closest at just 25 light-years away. Just to the right of Lyra and almost directly north, just above the horizon, is the constellation of Cygnus the Swan and its brightest star, Deneb. Deneb is one of the most luminous stars in the sky. It's a massive spectral type A blue-white supergiant, some 19 times the mass and over 100 times the diameter of the Sun. The star is somewhere between 55,000 and 196,000 times as luminous as the Sun. The huge range in luminosity estimate is caused by difficulty in determining Deneb's exact distance from us. Science's best estimates place it around 2,600 light-years away, give or take 212 light-years. Now, if you look high in the northern sky, you'll see the constellation Aquila the Eagle and its brightest star Altair. Altair is a spectral type A white star, located just 17 light-years away. It's about 10 times brighter than the Sun and has about 1.89 times the Sun's mass. Despite its size, Altair spins on its axis in just 10 hours. That compares to the Sun's 28-day rotation. These three stars we've been talking about, Altair, Deneb and Vega, form a stellar grouping known as the Summer Triangle. Not all that spectacular from southern skies, but for our listeners in the northern hemisphere, it's one of the best known stellar groupings. October also provides sky watchers with 3 meteor showers: the Draconids, the Taurids and the Orionids. The Draconids take place around October 8th. They're so named because their meteors appear to radiate out from the constellation Draco the Dragon, and so they're best viewed from the northern hemisphere. They're actually produced as Earth's orbit takes it through the debris trail left behind by the comet 21P, which takes about 6.6 years to make a single revolution around the Sun. The Taurids meteor shower peak on October the 10th, and as their name suggests, they appear to radiate out from the constellation Taurus the Bull. The Taurids meteors are composed of larger-than-average pebbles and dust grains, and are thought to be generated by debris from the comet 2P Encke, although it's thought that both the Taurids and Encke could be the remains of an earlier comet which disintegrated some 20,000 to 30,000 years ago, breaking up into several pieces and releasing material by normal cometary activity and possibly also by gravitational tidal interactions with the Earth and other planets. The Taurids debris stream is the largest in the inner solar system, taking the Earth several weeks to pass through it and resulting in an extended period of meteor activity compared to other meteor showers, which are usually over in a matter of days. Due to the gravitational perturbations of planets, especially Jupiter, the Taurids have been spread out over time, allowing separate segments labelled the Northern Taurids and Southern Taurids to be observable at different times in different hemispheres. The Southern Taurids are active from about September the 10th through to November 20, while the Northern Taurids are active from about October the 20th through to December 10. Next we have the Orionids meteor shower, which will peak on October 20. They're caused by debris from Comet Halley, which also causes the Eta Aquarids meteor shower in May. Comet Halley takes around 76 years to complete each orbit around the Sun. It'll next be visible from Earth in 2061. The Orionids are equally spectacular in both northern and southern hemisphere skies, with around 20 meteors an hour radiating out from the constellation Orion. The best time to see the Orionids is just after midnight, right before dusk. And now to continue our nocturnal voyage of the October skies, we're joined by Jonathan Nally, editor of Australian Sky and Telescope magazine.
G'day Stuart. October, beautiful time of the year to do stargazing, for people in the southern hemisphere at least, because the weather's getting nice and warm. With the hours of daylight getting longer though, of course we have shorter nights, but that doesn't matter because the weather really makes a difference, so you can get outside, it's not too cold, don't have to rug up quite so much. So as October begins, the Milky Way, which is the band of stars that is our galaxy seen from the inside, it's stretching from north to south in the western half of the sky after sunset. So you can see Sagittarius and the very impressive Scorpius, which really does look like a scorpion. They're easily visible there in the band of the Milky Way.
Yeah, but Sagittarius looks nothing like an archer.
Most things in the sky look nothing like what they're supposed to look like. You know, some of them do, like there's a triangular, looks like a triangle, 3 stars put together. That's really good. This is the point about the constellations, is the ancient constellations, it wasn't so much that people looked up, maybe Scorpius is different, but with the other ones, people didn't look up and say, oh, that looks like a such and such. Rather, they had their mythologies and they just put their characters into the sky and did the best job they could of joining the dots. Other more later constellations were named after famous inventions, pumps and those sorts of things. These days, who cares about a pump? But back in the day, a pump was a really amazing invention. Today, we would have the iPhone constellation, you know, and I don't know, the YouTube constellation or the Google constellation or something. So the constellations mostly didn't really need to look much like what they were supposed to. It was just a way of getting the mythologies and things into the sky. But Scorpius is one that really does look like a scorpion, yeah. So it's in the Milky Way in there, out to the sort of western half of the sky after sunset. But by midnight, that Milky Way will have disappeared, set below the horizon as the Earth has turned. What that means then is that the Milky Way's gone for a little bit in the sky tonight. And when we're looking up into the sky at this time of year, we're looking out of the plane of our galaxy, not through it. So there's a lot more empty space and fewer bright stars and things. So it might seem a little bit bare at first, but don't worry, there are still plenty of good things to see. So, for instance, for those of us in the southern hemisphere, we're coming into the time of year when the Magellanic Cloud galaxies are best seen. They're down there, way down south, about halfway up from the horizon, and there are 2 of them, the small cloud and the large cloud. And, of course, they're named after the explorer Magellan, the Magellanic Clouds. You'll need dark skies to spot them. They look like small clouds, and they're quite faint, so you need some dark skies. Don't try and do it from the middle of the city. But when you spot them, you'll be impressed because they're probably bigger than you think they're going to be. And these are the nearest sizable galaxies to us outside the Milky Way. So when you look at them, you think, oh, a little fuzzy bit of light. But when you think that's a whole galaxy out there and you're seeing it with your own eyes, that's pretty impressive, you know.
And they're getting smaller all the time because we're stealing more and more stars and gas from them.
Oh, we're a bully, aren't we?
Yeah, Milky Way is being accountable.
The strong crush the weak. That's how it works in the world, mate, and in the universe as well. Now, if you're out there tonight looking for the famous Southern Cross and you can't find it and you think you're going mad, well, don't panic. You're not going mad. At the moment, the Southern Cross is upside down, and it's either right on the southern horizon or even below the southern horizon from most populated southern latitudes, sort of in the very late evening up to about midnight or so. so. It does start to pop up again in the sort of south-east as the night gets on after midnight in the early morning hours. It sort of starts to rise up a little bit on an angle, but it's mostly lost from view at this time of year. In the late evening sky, you can see Saturn, the planet Saturn in the west, about a third of the way up from the horizon. At the beginning of October, it sets below the horizon at about midnight, so you've got a few hours after sunset to get out and have a look at it. By the end of the month, it's setting around 10:30 p.m., so it's getting lower and lower in the sky slowly as the weeks and months go on. Now, if you can't figure out which dot of light out there is Saturn, don't worry. If you've got clear skies on the 24th, October 24th, get out and have a look. Look for the moon, because the nearest bright thing to the moon will be Saturn on that particular night. And as I always say, if you know someone who's got a telescope, ask if you can come round and take a look at Saturn through it, because it really is quite specky. Now, if you like staying up late or getting up really early, the after midnight skies in October are really great. The other side of the Milky Way is starting to rise in the east after midnight, bringing with it lots of fabulous constellations, such as Orion, there's Taurus, Gemini, Canis Major, Puppis, and a bunch of others, all of which have really interesting stars or deep sky objects in them. So, for instance, Canis Major, the brightest star in the sky, is Sirius. Orion, famous Orion, has two bright stars, Rigel and Betelgeuse, and of course it also has the famous Orion Nebula, which you can see as a tiny smudge of light with the naked eye from dark skies. Don't stand under a street light or anything, but if you've got a bit of a dark sky, have a look. You might have to use what they call averted vision, which is where you don't look directly at it, you sort of look out of the side of your eye, and you should be able to see this little tiny smudge, which is the Orion Nebula, and of course grab some binoculars or a telescope and you get a much, much better view as well. As far as the planets go for this October, aside from the already mentioned Saturn, the cupboard's pretty bare, unfortunately, but if you're up shortly before sunrise and you have a clear eastern view, see if you can spot Venus and Mars really, really low down near the horizon. They'll be in the morning twilight, so Mars might be harder to see because it's not quite so bright as Venus. Venus is really bright, but they'll be really, really low down on the horizon, okay? I can't emphasize that enough. Only a few degrees above, so you can't have any trees and houses and those sort of things in the way, so find a clear patch or get yourself up a high on a hill or something. And you should be able to spot them if you've got some keen eyes. And that, Stuart, is October's night sky.
That's Jonathan Nally, the editor of Australian Sky and Telescope magazine. And this is SpaceTime. I'm Stuart Gary. And time now to take a brief look at some of the other stories making news in science this week with a science report. A new study has confirmed what most people have already noticed. Over the last 40 years, the waistlines of our kids have ballooned in Western nations. The new findings, reported in the Lancet Medical Journal, show that there are 10 times more obese girls and 12 times more obese boys now compared to 1975. Despite the overall rise, more young people remain underweight than obese. In some places, including Australia, New Zealand and North America, the average body mass index among young people has recently plateaued. But authors say this is not an excuse for complacency, highlighting the importance of tracking both food security and overeating. A new study has found that global warming caused by man-made hydrocarbon emissions is now killing off Nemo. A report in the journal Nature Communications has found that the clown or anemone fish, immortalised in the movie Finding Nemo, gets stressed out and reproduces less when its home anemone begins bleaching due to warming oceans. Bleaching is already well known in corals, but sea anemones can also bleach during heat waves. Researchers studied Great Barrier Reef anemone fish around French Polynesia during the unusually warm summer of 2016 and compared fish couples whose anemones bleached with those whose anemones didn't bleach. They found stress hormone levels were much higher in fish with bleached anemones, and they both spawned less often, and when they did spawn, they produced far fewer healthy offspring. In the world of renewable energy, one of the biggest drawbacks has been storage. Now a report in the journal Joule claims US researchers have taken on the challenge by developing a new battery that can use incredibly abundant and cheap materials such as sulfur, water, air and salt. The team say their new battery is capable of storing twice as much energy as lead-acid batteries, and it comes in at around just $1 per kilowatt hour, compared to between $10 and $100 for current batteries. However, there are drawbacks with the new sulfur battery. These include taking up more space than current batteries, and the fact that it operates for only around 1,500 hours, as opposed to the 5 to 20 year lifespan it would require. Sea lion numbers in the Auckland Islands of New Zealand are dropping because the mammals are dying after getting caught up in fishing nets. A report by the University of Otago published in the PNAS found the deaths are still occurring despite the introduction of exclusion devices to sub-Antarctic squid trawlers, which were intended to reduce the number of sea lions being caught. The researchers found there's absolutely no evidence to support claims that these devices reduce the number of sea lions being killed. In fact, the use of the devices actually obscures the total number of sea lion deaths. The sea lion is an endangered species, and current management has been focusing on keeping pups healthy rather than on the impact of fishing. A new study claims that whether a man finds a woman's scent alluring may have nothing at all to do with compatibility between their immune systems. Previous studies looking at pheromones have suggested people are drawn to partners whose immune systems best complement their own, leading to kids with the best possible immunity to disease. The new study, reported in the Proceedings of the Royal Society B, involved men being asked to smell female body odours collected when the women were at the most fertile part of their cycles. The males were then asked to rate the attractiveness of women based purely on smell alone. Researchers found that while men did prefer some women's odours over others, they found no correlation with how similar or different the pair's immune systems were. And finally for now, scientists have analysed People magazine's list of the world's most beautiful back to 1990 to see how Homo sapiens' idea of beauty has changed. Reporting in the Journal of the American Medical Association Dermatology, researchers found that people in 2017 now include a wider variety of skin colours and older age groups among those deemed to be the most beautiful in the world compared to 27 years ago. The average age of celebrities who made the list increased from 33 years in 1990 to almost 39 years of age in 2017. And the proportion of people from non-white races also increased from 24% in 1990 to 40% in 2017. The researchers say this shows beauty standards are evolving as people learn how to integrate the effects of media with exposure to new cultures and different norms. You're listening to SpaceTime, I'm Stuart Gary, and that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, Audio Boom, YouTube, from spacetimewithstuartgary.com, or from your favourite podcast download provider. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. If you want more SpaceTime, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and other things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one worded in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, at SpaceTime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/spacetime with Stuart Gary.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.